Spiral galaxies. Spiral galaxies are among the most recognizable structures in the universe, shaped like vast rotating pinwheels stretching across space. They contain a flat, rotating disk made up of stars, gas, and dust, all winding outward from a bright central bulge. In the center, older stars are usually packed tightly together, giving the core a warm yellowish glow, while the spiral arms are filled with younger, hotter blue stars. These arms are not rigid structures, but rather density waves, regions where matter is slightly more compressed, encouraging new star formation. Our own Milky Way is a spiral galaxy, which makes this structure especially important for understanding our cosmic neighborhood. Spiral galaxies tend to form in regions where gas is abundant, and angular momentum allows material to settle into a rotating disk. Over time, their arms can stretch, twist, and evolve depending on gravitational interactions with nearby galaxies. They matter because they are active sites of star formation, continuously producing new generations of stars, and sometimes planetary systems like our own.
Barred spiral galaxies are a variation of spiral galaxies where a straight bar of stars cuts through the central bulge before the spiral arms begin. This bar structure is not just visual, it plays an important role in channeling gas toward the galaxy's center, often fueling star formation or even feeding a central black hole. The spiral arms typically extend from the ends of the bar, creating a distinctive S or cross-like pattern depending on the viewing angle. Scientists believe that nearly two-thirds of spiral galaxies, including the Milky Way, may actually be barred spirals. The bar itself forms due to gravitational instabilities within the galactic disk, redistributing angular momentum over long periods of time. These galaxies are important because the bar acts like a cosmic conveyor belt, shaping how stars and gas move throughout the system. Over billions of years, the presence of a bar can change the entire evolution of a galaxy's structure and star-forming activity. Elliptical galaxies. Elliptical galaxies appear smooth, featureless, and rounded, ranging from nearly spherical shapes to elongated ellipses. Unlike spiral galaxies, they do not have distinct arms or visible structure, and their stars move in more random orbits rather than organized rotation. Most elliptical galaxies contain older, redder stars with very little cold gas or dust available for new star formation. This gives them a more passive and aging appearance compared to the active star-forming spirals. They're often found in dense galactic environments, like clusters, where frequent gravitational interactions can strip away gas and disrupt structure. Many elliptical galaxies are thought to form through the merging of smaller galaxies, a violent process that scrambles stellar orbits into their current smooth shape. Their importance lies in showing the end stages of galactic evolution, where star formation has largely ceased and only long-lived stars remain. In the largest cases, known as giant ellipticals, they can contain trillions of stars and dominate the centers of galactic clusters. Lenticular galaxies sit between spiral and elliptical galaxies, acting like a transitional form in cosmic evolution. They have a central bulge similar to ellipticals, but also a faint disk structure like spirals, although without prominent spiral arms. Most of their gas has been depleted or stripped away, leaving behind older stellar populations and little active star formation. From a distance, they can appear smooth like ellipticals, but closer observation reveals their disk-like shape. Scientists believe lenticular galaxies may be former spiral galaxies that lost their gas through interactions or environmental effects in dense clusters. Alternatively, they might form through mergers that preserve some disk structure. Their significance lies in representing a middle stage in galaxy transformation, showing how dynamic and changeable galaxies truly are. They remind us that galaxies are not fixed objects, but evolving systems shaped by both internal processes and external forces.
Irregular galaxies. Irregular galaxies are galaxies that do not fit into any clear shape or category, appearing chaotic and asymmetric in structure. They often lack a defined spiral arm or central bulge, giving them a fragmented and disturbed appearance. Many irregular galaxies are rich in gas and dust, making them active regions of star formation despite their disordered structure. Their irregular shapes are often the result of gravitational interactions, such as close encounters or collisions with other galaxies. The gravitational forces distort their structure, pulling stars and gas into uneven distributions. Some irregular galaxies, however, may never have formed a structured shape in the first place, especially smaller ones in the early universe. They are important because they show us what galaxies can look like under strained gravitational stress or in early developmental stages.
The large and small Magellanic Clouds, companions to the Milky Way, are classic examples of irregular galaxies visible from Earth. Dwarf spheroidal galaxies. Dwarf spheroidal galaxies are small, faint galaxies with little to no gas and very low rates of star formation. They're typically found orbiting larger galaxies, like satellites, bound by gravity, but often stretched and influenced by their massive neighbors. Their stars are dominated by spherical or slightly elongated shape, but without the brightness or structure of larger systems. These galaxies are dominated by dark matter, making them important objects for studying the unseen mass of the universe. Because they contain mostly old stars, they provide a kind of fossil record of early star formation. Their low brightness makes them difficult to detect, and many were only discovered in recent decades using deep sky surveys. They matter because they help astronomers understand galaxy formation on small scales and the role of dark matter in holding galaxies together. Despite their size, they are key pieces in the puzzle of cosmic structure. Dwarf irregular galaxies. Dwarf irregular galaxies are small galaxies that maintain a chaotic, unstructured shape, but differ from dwarf spheroidals by containing significant amounts of gas and active star formation. They often appear as scattered collections of bright star clusters embedded in gas clouds. These galaxies are usually isolated or only weakly influenced by larger galaxies, allowing their irregular structure to persist without being shaped into a more defined form. They are thought to resemble some of the earliest galaxies in the universe, when structure had not yet fully developed. Their simplicity makes them valuable for studying star formation in relatively unprocessed environments. Even though they are small, they contribute to the overall population of galaxies in the universe and play a role in chemical enrichment through repeated cycles of star birth and supernova explosions. Dwarf elliptical galaxies. Dwarf elliptical galaxies are small, low-luminosity versions of elliptical galaxies, sharing their smooth shape, but on a much smaller scale. They contain mostly older stars and very little gas or dust, which limits new star formation. These galaxies are often found in clusters or as companions to larger galaxies, where gravitational interactions have stripped away much of their original material. Their simple structure and lack of active processes make them relatively stable and long-lived. Despite their small size, they are among the most common types of galaxies in the universe. They provide important clues about how galaxies evolve under environmental pressure, especially in dense cosmic regions. Many are thought to have once been dwarf irregular galaxies that lost their gas over time, transitioning into a quieter, more passive state. Their study helps astronomers understand how external forces shape the smallest building blocks of galactic systems. Starburst galaxies. Starburst galaxies are galaxies undergoing an extremely high rate of star formation compared to typical galaxies. In these systems, gas clouds collapse rapidly, producing massive numbers of new stars in a relatively short period of cosmic time. This intense activity often concentrates in the central regions, though it can also spread throughout the galaxy, depending on the trigger.
Starbursts are commonly caused by interactions or collisions with other galaxies, which compress gas and ignite star formation on a large scale. The result is a brilliant, luminous galaxy dominated by young, hot stars and glowing nebulae. However, this phase is usually temporary because the rapid consumption of gas eventually exhausts the fuel needed for new stars. Starburst galaxies are important because they show how dramatically galaxy evolution can accelerate under the right conditions. They also help explain how some galaxies build up large portions of their stellar mass in relatively short periods. Ring galaxies! Ring galaxies are rare and striking systems where stars and gas form a distinct ring-like structure, often with a relatively empty or less dense center. They are typically created when a smaller galaxy passes directly through the center of a larger disk galaxy, generating gravitational waves that push material outward. This outward-moving wave compresses gas, triggering star formation in a circular pattern that expands over time. The result is a glowing ring of young stars surrounding a quieter core. Because this configuration depends on a precise type of collision, ring galaxies are uncommon and often temporary. Over time, the ring may distort or dissolve as gravitational forces continue to reshape the system. These galaxies are valuable because they provide clear visual evidence of galactic collisions and wave-like propagation of star formation. They reveal how dynamic and responsive galactic disks can be when disturbed.
Peculiar galaxies. Peculiar galaxies are galaxies with unusual shapes or features that do not fit standard classification systems. Their irregular appearances are usually the result of interactions, mergers, or internal disturbances that disrupt normal galactic structure. They may show warped disks, tidal tails, or asymmetrical brightness patterns that indicate past gravitational encounters. These galaxies often represent transitional stages in galactic evolution, where structure is being actively reshaped. While they are not a single defined category with consistent properties, they are unified by their deviation from typical forms. Many well-known peculiar galaxies are in the process of merging, offering snapshots of dynamic cosmic events. Their importance lies in showing that galaxy morphology is not fixed, but constantly influenced by environmental and internal forces. Studying them helps astronomers reconstruct the history of galactic interactions. Ultra-diffuse galaxies. Ultra-diffuse galaxies are extremely faint galaxies that spread their small number of stars over a very large area, making them difficult to detect. Despite their size, they contain relatively few stars, giving them a ghost-like appearance in deep space observations. Many are found in galaxy clusters, where they may have been stretched or stripped by gravitational interactions. Their low brightness makes them challenging to study, and they were only confirmed in large numbers in recent years with advanced telescopes. Some ultra-diffuse galaxies appear to contain large amounts of dark matter, helping them maintain structure despite their sparse stellar content. Others seem fragile and may not survive long in dense environments. They are important because they challenge traditional ideas about how much matter is needed to form and sustain a galaxy. Their existence expands our understanding of the diversity of galactic structures in the universe. Active galactic nuclei galaxies. Active galactic nuclei galaxies are galaxies whose central regions emit enormous amounts of energy due to material falling into a supermassive black hole. This process creates a compact but extremely luminous core that can outshine the rest of the galaxy. The energy is produced as gas and dust heat up while spiraling inward, forming an accretion disk around the black hole. These galaxies can emit radiation across the entire electromagnetic spectrum, from radio waves to X-rays. The activity can vary over time, sometimes increasing dramatically depending on the availability of material. Not all galaxies show this behavior, but when they do, it fundamentally changes how we observe them.
active nuclei are important because they demonstrate the connection between galaxy evolution and black hole growth.
They also influence their surroundings by releasing energy that can regulate star formation.
Ciphered galaxies! Ciphered galaxies are a specific type of active galaxy characterized by bright, energetic cores with strong emission lines in their spectra. Unlike the most extreme active galaxies, Cyphers are typically spiral galaxies that host moderately active central black holes. Their nuclei can vary in brightness, sometimes changing over relatively short timescales in astronomical terms. The surrounding galaxy often retains its spiral structure, meaning that star formation and galactic disk features remain visible.
The central activity is believed to be driven by gas falling into a supermassive black hole, releasing energy as it heats up. Safer galaxies are important because they provide a closer and more accessible example of active galactic nuclei in relatively nearby galaxies. They help astronomers study how black hole activity interacts with normal galactic structures. Their balance between activity and structure makes them a key bridge between quiet and highly energetic galaxies.
Quasars. Quasars are among the most luminous objects in the universe, powered by supermassive black holes consuming vast amounts of surrounding material. At their peak, a quasar can outshine entire galaxies, emitting enormous energy from a region smaller than our solar system. This extreme brightness comes from the accretion disk surrounding the black hole, where matter is heated to incredible temperatures as it spirals inward. Quasars are typically found in distant galaxies, meaning we observe them as they were in the early universe. This makes them valuable tools for studying cosmic history and galaxy formation. Despite their intensity, they are not permanent stages, but rather active phases in a galaxy's life cycle.
Over time, as the black hole consumes nearby material, the quasar activity fades. They matter because they reveal the relationship between black hole growth and the evolution of early galaxies.
Blazars. Blazars are a type of active galaxy where one of the relativistic jets from a supermassive black hole is pointed directly toward Earth. This alignment causes the emission to appear extremely bright and highly variable across all wavelengths. The jet is composed of charged particles moving at nearly the speed of light, producing intense radiation through various physical processes. Because of this orientation, blazars can change brightness rapidly, sometimes within hours or even minutes. They are among the most energetic phenomena in the universe, often detected in gamma rays. Despite their extreme behavior, they are fundamentally similar to other active galactic nuclei, with the difference lying mainly in perspective. Blazars are important because they help astronomers understand jet physics and relativistic effects in extreme environments. They also serve as natural laboratories for studying high-energy astrophysics.